In this video, we're taking the properties that we observed in the activity in class and using them and or proving them. So yes, you can skip through a little bit of this video if you were here for the activity and those properties made sense, but most of this video is proof and application, so you'll want to pay attention. This part C that you see on the screen, it's on page 419, but it's referring to the diagram on page 420, so I apologize for that. It's asking you to identify the opposite sides and opposite angles. So the opposite sides are AB and CD, and BC and AD. The opposite angles are angle A and angle C, and another pair of opposite angles is angle B and angle D. And in the activity in class, we noticed that as we manipulated the parallelogram, we noticed that the opposite sides are congruent and opposite angles are congruent. And then it asks us to notice something about the diagonals of a parallelogram. And if the activity went as planned in class, then we talked about how the diagonals intersect each other at each other's midpoint. That means that we can say that the diagonals bisect each other. In other words, they cut each other into congruent segments. We also talked about consecutive angles, such as angles A and B, or angles A and D in the figure in your textbook. And in the activity in class, we noticed that no matter how we wiggled those angles, those consecutive angles were supplementary. So in this question 2, it says, a student claims that the perimeter of triangle AEB in the construction is always equal to the perimeter of triangle CED. Without doing any further measurements, explain whether or not we agree with the student's statements. Well, if we look at triangle AEB and we look at triangle CED, well, we know that AB is congruent to CD. We know that CE is congruent to AE, and we know that BE is congruent to DE. So, yes, we agree with the student's statements because those two triangles are congruent. By side, side, side. So let's talk about how using congruent triangles can allow us to prove some of the properties that we discovered about parallelograms. So our first theorem here is that if a quadrilateral is a parallelogram, then its opposite sides are congruent. So in this proof, we are given that this is a parallelogram, and then they draw segment DB, because through any 2 points I know there's exactly one line. I'm allowed to draw an auxiliary line. In statement 3, we're saying that AB is parallel to DC and AD is parallel to BC. I hope that you would realize that since this is a parallelogram, that these lines are parallel because of the definition of parallelogram. And in the future, you'll probably see me abbreviate parallelogram with the symbol for parallelogram. And then it says angle ADB, that's this angle, is congruent to angle CBD, this angle. And also that angle ABD is congruent to angle CDB. What I really hope you're starting to notice and that things are starting to come together for you is that these are alternate interior angles. So these angles are congruent because of the alternate interior angle theorem. I know that DB is congruent to DB. I hope you haven't forgotten our good friend reflexive property of congruence. And so I'm saying in reason 6 that I'm using angle, side angle, triangle congruence theorem. And I hope by now you take that as a huge hint to say, oh, I'm saying that two triangles are congruent. And those two triangles are triangle ABD and triangle CDB. And then again, hopefully you remember that when we go further than saying that two triangles are congruent and we say that parts of them are congruent, we're using CPCTC. Corresponding parts of congruent triangles are congruent. The next conjecture that we made is also a theorem that the opposite angles of a parallelogram are congruent. And I hope that you would notice that these proofs start to look a whole lot alike. I'm given that ABCD is a parallelogram. They drew segment BD because through any 2 points, there exists one line. I know that AB is parallel to DC and AD is parallel to BC. Again, definition of parallelogram. Alternate interior angles theorem, we saw that earlier. Angle ABD congruent to angle CDB. Angle ADB congruent to angle CBD. Segment BD is congruent to itself because of the reflexive property. These triangles are congruent, ABD, and CDB. And this time, we're using this to say that angle A is congruent to angle C, but we're still using CPCTC. So I hope that you're starting to notice that some proofs, when we're dealing with parallelograms, will start to look a lot alike. Explain how the proof would change in order to prove angle B congruent to angle D. Coming back to the diagram, if I'm trying to prove that angle B is congruent to angle D, perhaps I wouldn't draw the auxiliary segment BD. Perhaps I would draw the auxiliary segment AC. Back in Reflect 1, we realized that the consecutive angles of a parallelogram are supplementary, and this can be stated as a theorem. If a quadrilateral is a parallelogram, then its consecutive angles are supplementary. Explain why this is true. Well, let's consider this parallelogram. In this parallelogram, angles A and B are consecutive angles. Now, if I extend those sides and I extend this side that's going through them, what I'm hoping you're starting to remember is the river and the bridge, and angles A and B. These two angles are on the same side of the bridge. They are inside the river, and that makes them same side interior angles. Consecutive angles of a parallelogram are supplementary because they are same side interior angles. With respect to parallel lines. The last theorem, if a quadrilateral is a parallelogram, then its diagonals bisect each other. And we're proving this as well in a different format. But if you're looking at it carefully, I really hope that you notice it's a lot of the same stuff, okay? However, in the last proof, it was kind of obvious what triangles we were eventually going to say were congruent because there were only two triangles in the diagram. This is a little bit more challenging because there's more triangles to choose from. So let's talk about what we're trying to prove and maybe work backwards from that. So we're trying to prove that AE is congruent to CE, so that's those two segments. We want to prove that BE is congruent to DE, and what I want you to notice is the two triangles that I can show are congruent that would eventually lead me to say that those segments are congruent. I know that AD is congruent to BC because they're opposite sides of a parallelogram. We've already proven that they're congruent, so we're going to use that property now. And you see that being used here. Okay? And you notice the alternate interior angles. Hopefully you see them again. And so now we kind of have a clear picture in our mind that this triangle and this triangle are the ones that I'm interested in. Okay, so again, I'm given that ABCD is a parallelogram. By the definition of a parallelogram, I know that I have parallel sides, and I need both pairs of parallel sides in order to show both pairs of alternate interior angles. So I'm still saying that AD is parallel to BC and that AB is parallel to CD. We already talked about how we can say that AD is congruent to BC because they're opposite sides of a parallelogram, so we know that they're going to be congruent. And we talked about the alternate interior angles, same as the last two proofs. Angle DAE is congruent to angle BCE. The only reason we're naming it a little bit differently is because we have the E in the figure separating the two triangles. but they are the same angles that we talked about in the last two proofs. So that's one pair of angles, and then I also have angle ADE congruent to angle CBE. And so there's three parts of those two triangles, and if it's not clear why it's angle side angle, let me mark this up for you. This angle is congruent to this one, this guy to this one, this side is congruent to this side. So I have two pairs of angles, two A's, and I have one pair of sides, and the sides are between the angles. Okay, so triangle ADE is congruent to triangle CBE. And now I can say that which I set out to prove, which is that AE is congruent to CE, and BE is congruent to DE. So now we're taking that information and applying it. You'll notice in example 4, part A, I'm asked for the length of segment AD. So notice that the length of segment AD is the 7x. It's going to equal 5x plus 19 because those two sides, AD and BC, are opposite sides of a parallelogram. So they set those equal to each other, solve for x, plugged the 9.5 back in, and found that the length of AD was 66.5. In order to find angle B, in part B, we're going to use the fact that opposite angles of a parallelogram are congruent, so angle B is congruent to angle D, and therefore the measure of angle B has to equal the measure of angle D. So that means that 6y plus 5 will equal 8y minus 17. And when I solve that equation, I get 2y equal to 22, so y is 11. And when I take that 11 and plug it back in, I have 66 plus 5, which is 71. Suppose we wanted to find the measures of the other angles in parallelogram ABCD. Well, if I already know that angles B and D are 71, angles A and C have to be supplementary to that because angle A is a consecutive angle to angle B. So they're supplementary. Minus 71 equals 109. So the measure of angle A would equal 109. That would also equal the measure of angle C. Since angle A and angle C are opposite angles. And therefore, they are congruent. In this example 8, we're asked to find the length of QR. So notice that QR is a side of the parallelogram, and we know that opposite sides of a parallelogram are congruent. So we can set up the equation 2z plus 4 equals 3z minus 4. And when I subtract 2z from both sides, I get z on the right-hand side. I add 4 to both sides, and I get that z equals 8. Remember, please remember that the problem wasn't asking you for the value of z. The problem was asking you for the measure of QR. So QR equals 3 times z minus 4, which is 20. I like example 9. It's asking for the length of PR. Well, PR is a diagonal. And a diagonal isn't necessarily congruent to anything else. However, the two parts of the diagonal are congruent because remember, the diagonals intersect at each other's midpoint. So that means that since PT equals RT, my equation would be x plus 9 equals 4x minus 6. When we subtract x from both sides, we have 3x. We add 6 to both sides, we have 15. When we divide both sides by 3, x equals 5. Again, remember that you weren't asked for the value of x. You were asked for the length of PR. Well, PR I hope you would realize equals x plus 9 plus 4x minus 6. So I have to take x and plug it into both of those. So now I have 5 plus 9 plus 4 times 5 minus 6. So work that all out, and it's 28.